Sorry, what? Oh, it is. Same. Both of them have two topics. Okay, anyways, everyone. Nothing bad.
Is my finals so this is going to be 2 weeks.
In 2 weeks, cover art for new space.
Then space
Okay, good. That's why I want to cover this today. Okay, everyone. As I was saying, right, last week we learned about the simple structures of atom. We learned about nucleon number, proton number, elements, go for experiment. This week we're going to learn about radiation. Okay, to be very specific, there's only 3 forms of radiation in your syllabus, which is known as alpha, beta, and gamma. Okay, now each and every one of these radiation, they have their own characteristics. First and foremost, if we talk about detection-wise, alpha could be detected by a cloud chamber, whereas beta and gamma could be detected by a Geiger-Müller tube. But you don't need to remember the name because obviously it's too long of a name, right? Instead, in your exam, you just need to remember GM tube. Okay, so what does a cloud chamber look like and how does a GM tube look like? Let me show you. I was watching this dog with 4.9 million subscribers and bro, that's crazy. Anyways, like I was saying, a cloud chamber looks something like this. This is a Petri dish. This is basically just a Petri dish, and then this one here is the alpha radiation source. Okay, you'll notice that as this thing emits alpha radiation, it is very similar to fighter jets flying across the sky and leaving a trail of cloud behind, as you can see here. You see all these small little specks on the glass? These are basically alpha particles. Alpha particles. It's a form of radiation. Like for example, smoke detection. Mostly smoke detection. It's a form of radiation. It's not a gas form. It's like a down, where it's like a radiation. Like imagine the sun, right, radiating infrared radiation towards us. You won't be able to see infrared, right? But you can feel it. But this one, you'll only feel it 10 days later when you die. Like for example, if you're exposed to overexposure to radiation, will cause you to die slowly from the inside out. And you start by losing hair, weight, and then your life. Okay, so it's a form of radiation. Okay, so you can see that this alpha particles is being shot up by this alpha radiation source, beryllium or whatever. And this whole thing inside a Petri dish is known as a cloud chamber. It's very small only. It's probably the size of the Petri dish. Okay, so this is what a cloud chamber looks like. And then a GM tube, just is those things that you see on cartoon, the hazmat suits, and then they'll take something to go like from there. This is detect beta. Actually, this can detect all forms of radiation, like alpha, beta, and gamma. Okay, so let's say for example, if you're reading it, let's say for example today you're reading it in this room, right? You probably just read some very low background radiation only. But if you go to a very radioactive site, for example, when Hiroshima and Nagasaki got bombed, right? If you take this thing, this GM tube will spike like crazy, and the reading will go all the way again. Okay, so this is called a GM tube. You don't need to remember the full name. You need to remember it's called a GM tube. That's all. Okay. So obviously they have their own symbols as well. Alpha is actually a tail A. It's not a capital A, guys. It's a tail A. It looks something like this. Okay. Beta is a tail B, and gamma is the reverse of Cancer symbol. The Cancer symbol is like this one, right? Yeah, the pink ribbon that you see, right? This is the opposite, like the reverse. Okay. In terms of its elements, alpha particles are helium. This is a small e, by the way. Helium 42. Beta is electron 0, -1, and gamma, because it is part of the electromagnetic spectrum, it is just a gamma ray. Okay, in terms of its charges, alpha is positively charged. Right now, you know that it's +2 charge, beta is -1 charge, and gamma is 0 charges, no charges. Now, this charges is directly related to the ionizing power, right? For example, because this is +2, it can steal 2 negatives, right, from other neutral atoms. So it is very strongly ionizing. Every 1 alpha particle can steal 2 negative charges. Beta only -1, right? Means to say it can steal 1 positive charge from other neutral atoms, right? So because of that, it is relatively weak, and gamma has no charges, so it has no ionizing power. Okay, and then of course, in terms of the mass, you don't need to remember these numbers. You just need to remember that alpha is like that fat kid. Okay, it is the heaviest. Beta is much lighter, right? And gamma, because it is a photon, so it has no mass. Okay, you need to remember this is the heaviest and this is the lighter one, which you'll be tested later on. In terms of the range, alpha particles, just like the fat kid, cannot run very far. Hey, this is not discrimination, it's just physical facts. I'm not, don't put racism in this stuff, right? So, okay, so anyways, the alpha particles don't travel very far. They just travel a few cm in that factory dish I showed you. Beta can travel a few meters, and gamma is just like radiation, it travels unlimited. Okay, in terms of the speed, you need to know that this guy runs the slowest, 10% the speed of light, 90% the speed of light, and gamma is the speed of light, because once again, it's electromagnetic waves. In terms of the ionizing, like I mentioned, strong, weak, weakest. Okay. Okay, don't copy first. I'll give you time to copy what? Speed of light. No, 这个是 traveling at the speed of light, which is 3 times 10 to the power of 8. 这个是 90% the speed of light, this is 10% the speed of light. Okay. Then in terms of the penetration power, okay, guys, alpha is the weakest in terms of its penetration power. Even a piece of paper and even smoke particles cannot penetrate through already. Okay, mean to say if I got alpha particle here, I put my hand here, right? It cannot penetrate through. All here will be empty already. If I have a detector here, 0 already. But beta will penetrate through relatively stronger. It will be usually stopped by aluminium or thick pieces of wood. Okay, in your exam, if you see the word aluminium or wood, right, usually they're trying to test your understanding of beta already. Okay, and gamma is the strongest penetration power of them all. You usually have to be stopped by thick lead. Okay, it has to be stopped by relatively thick lead. The one in your pencil. Yeah, like the lead, like literally the lead in your pencil. Huh? No, this one it has to be very thick lead to stop the gamma, but this is obviously not thick, bro. Right. Okay. Okay, so if you see these words, usually it's trying to test your understanding of penetration power. In terms of the electric field, okay, if I have a positive charge here and a negative charge plate here, right, what happens is the beta will be deviated towards the positive plate, whereas the alpha will be deviated towards the negative plate, because obviously the opposite charges attract, right? Okay, now I want to ask one question. Do you notice that the beta actually deviates more than the alpha? Why? Yes. The beta deviates more than the alpha. Why? Because alpha is full charge. So because it has lower. No, everyone's wrong. It's because alpha is a fat guy. Okay, it's harder to push him around. So that's why he deviates much less. Imagine today, right? If you push me and you push Macy, right? Who's going to move more? Obviously, Macy is going to move more, right? Because I'm the fatter kid, right? So this is the exact same thing here also. Alpha is the fatter kid, right? Then obviously alpha is harder to move with the same electric field strength. Okay. But even if it's more momentum, it's harder to change direction, right? Like a lorry and a Ferrari, right? So it's the same concept. It's because of the mass, it's heavier to deviate. And gamma has no charges, so it just shoot straight through. Okay, now this is the important one that you'll see in the exam. They usually will test you on this one now, if anything. Right. They'll say that, okay, listen up, this is the effects of a magnetic field. Imagine today I have a magnetic field that goes into the paper. Do you know what that means? It means to say my north is in front of my screen and my south is behind my screen. Okay, listen up carefully. If magnetic field is going into the paper as represented as X here, my north pole is in front of the screen. Okay, my south pole is placed behind the screen. Then what magnetic field can go into the paper, go into the screen, right? Right. You understand what I'm talking about? Which
Yeah, not that.
do you know what does magnetic field going into the paper mean? The magnetic field is like this, going into the screen. Right. In order for the magnetic field to go into like this, where should I place my north pole? It should be north pole here and south pole here, right? Then it will go into the screen, right? Make sense? Okay. Okay. Then once you understand this, the next thing you need to associate is that alpha is like current and beta, which is an electron, is literally an electron. Okay. Look here, if I have magnetic field and I have current, this looks kind of familiar. Yeah, it's very good. Exactly. You're supposed to use the Fleming's left-hand rule here. Because if you recall the Fleming's left-hand rule, for those who don't recall, don't worry, let me open up here. Right, left-hand rule said what? You must be given the magnetic field and the current to find the force acting on the wire, right? This one here is exactly that. Okay, I'm given the magnetic field, I'm given the current, I need to find the force acting on it. So using my Fleming's left-hand rule, for those who are online, pay attention now. Using my Fleming's left-hand rule, my index finger will point into the screen, right? Because my finger is going in now. And then if I look at my alpha, if let's say alpha is shifting in this direction, right? Alpha is like current, right? It means to say my current is going to the right, right? If it's going to the right, that's not your left hand. If it's going to your right, it means to say that my force will be upwards, right? Right. So I know that alpha particles will be deviated upwards. Okay, right. And then what if I have beta particles in this direction? Just like I said, beta particles are like electrons, right? If electron is moving in this direction, then current will be the opposite, right? Because electron flow and current flow is opposite of each other, right? So magnetic field into the screen, current to your left, right? You'll notice that your force is going downwards, right? That's why the beta particles will deviate downwards. And once again, you notice that the beta particles deviate more than the alpha particles. Why again? Yes, because this is the lighter element and this is the heavier element. Okay, everyone? Anyone has any questions with this part here? No? Zero? Good. Copy everything now. Come on. No, you have to say it's not heavier. Yes, the relative point.
Okay.
Let's see and so.
Okay.
Let's see. 我那个实验什么？哦，你说我也做。
因为或者可以 okay, if my friend again it will complete I can then if the rest will be much more than guarantee it I get the money. Sleep level, I get about 2%.
House around this.
And this are the things not like you did spend with friend everything on clarification. Inventory by as well as team like
No. CM 来的
range bro，差不几远，
CM
它只是可以 travel a few cm away 那种。Yeah, it will only travel a few cm by maximum in cm. The beta will travel a few meters. Gamma 就是好像 like 这样子咯 unlimited 咯。Oh, no. Range. Okay, everyone. Done. Okay, then the next part we talk about is basically radioactive decay. Radioactive decay is okay, imagine this no. Yeah, something to do with half-life, but before that. Okay, so let's say for example today I have a random element X okay, with 100 nucleon number and 50 proton number. Usually, we will categorize this first atom as the parent nuclei. Okay, it's usually unstable. Okay, so in order for it to achieve a stable state, it has to go through some form of decay, either alpha decay or beta decay. For example, if let's say it goes through alpha decay, right, the first element it will spit out is basically the alpha particle, which is helium-4 okay, and this will cause it to turn into the daughter nuclei, okay, which is the more stable one, okay, and the mass and everything will all still be the same. So if it's 100 here is 4 already, right? Here will be 96. If it's 50 here is 2 already, right? Here will be 48. This is what we call the daughter nuclei, which is the more stable one. Yeah, you have to write the symbols. I'm just giving a random example. No, you'll be given the periodic table. Yeah, if they ask, okay. So this thing could also go through a beta decay, right? If let's say it goes through a beta decay, then the first element is going to spit out is the electron 0, -1, which is the beta element, right? Plus the new daughter nuclei. But obviously, it won't be the same thing, right? Because this is Y already, and the other one will be the Z. So 100 minus 0 will be 0. 50 minus 1, is it 49? Oh, sorry.
51.
It's 51. Right. A lot of students, they get this wrong. Because you must always remember it's minus. So 50 minus 2, 48, right? 50 minus -1 will become 51 here. It becomes 51 here. Yeah, it's a bit of algebra. Right. So yeah, these are the decay process. Okay, in your exam, if they ever ask, right? So let's say for example, I give one example. Let's say for example here, this PO, right? Okay, it goes through alpha decay. Okay, alpha decay, the first thing I write is the alpha element helium-4 right? Then I minus the numbers 2, 0, 6, and 92. Okay, sorry, 82. Then 82, I don't know what element is, right? I refer to the periodic table. Which one is 82? Which one is 82? Oh, PP11. Right, so just right here. But usually, if they test, they will ask you for the element one. They will just ask you for the nucleon number and proton number. Okay. So if you look at the definition here, it says that a radioisotope, an unstable arrangement of neutrons and protons in the nucleus, is altered to become a more stable arrangement. Usually, the parent nucleus becomes the daughter nucleus and a particle, which could either be the alpha element or the beta element. Okay. Isotopes of an element may be radioactive due to the excess of neutrons in the nucleus and or the nucleus being too heavy. Okay, if you think about it, right, beta decay is actually a conversion from neutron to a proton, right? Because if you look here, if you look at my symbol here, right, just now, it's 51, right? Right now, if I look here, there's 50 proton and 50 neutrons, right? If it goes through a beta decay, it will become 51 protons and 49 neutrons. If you compare it here to here, right, you'll notice that actually the proton is converted, the neutron is converted into the proton. That's why the numbers decrease here. This is essentially what a beta decay is. They convert the neutron into a proton. Okay? Everybody? So if you look at the notes here, it kind of makes sense. Okay. Excess neutrons, convert it into. Okay, attempt the questions below. Everybody.
How do you read it?
Yes.
When you read periodic table, like the total number is.
Yeah. You can double check, let's say, right? Sure, right? Check this one. Before it, you look here, is it equal to people? Then it means it's what we should know. So.
Okay, what about this? Like on the. Uh, yes, seven, six.
Seven, it's a good. Well, it's.
Yeah.
It's.
Okay, everyone. Quite straightforward. I don't think we need to go through this okay. Just make sure that when you do the beta particle one is 0, -1. And then here is 7 and 14. It should be nitrogen. Okay. Quite straightforward, quite straightforward. Okay, this is the important one that we're supposed to cover today, which is half-life decay. Okay, this is very important, by the way. For sure, come out in your paper 2 may have a very high chance, like I would say up to 80% come out in your paper 4. Okay, this one is very important, pay attention. So what is half-life there? Half-life is basically, like the name suggests, the time taken for the radioactive decay to decay by half its current amount. For example, let's say for example today I have some random radiation right, that has, let's say, 100 counts per minute. Counts per minute is the amount of radiation that it emits out every minute. So it's like, let's say 100 counts per minute. Okay. If let's say I say that this radioactive substance has a half-life of 3 days, where the half-life is 3 days, it means to say it takes 3 days for it to decay by half its current amount. 3 days. What if another 3 days goes by? Does it become 0? It becomes 25 because like I said, the keyword is half its current amount, not the previous amount. And you just keep going half only. It will never be minus exact one number one. Another 3 days go by, it'll be 12.5. Another 3 days go by, it'll be 6.25. Another 3 days go by, it'll be 3.125, and so on, so on, so on. Okay. So what is the application of half-life? Half-life is actually used for carbon dating. You know, like for example, when you take all the dinosaur bones and you see how old the thing is, right? It doesn't write made in 1992, right? How do the scientists actually find out how old it is? Is by counting the amount of carbon in the bone. Okay, so all human living things will keep absorbing carbon and releasing carbon at the same time. So like for example, at any point of time, if let's say I die right now and you test my bone for carbon, right, you'll have 100% carbon. But let's say after after one half-life, right, I'll only be left with 50% of my carbon, and another 50% after another half-life, another 50, and so on, so on. Okay, so by backtracking this process, they basically find out how old the bone is now. Okay, so yeah, half-life, like I mentioned, is the time taken for half the nuclei of an isotope to decay. The current amount, not the previous amount. Using half-life, you can predict the amount of radiation materials to be given out after a certain amount of time. It is used for carbon dating, calculate how long do I need to store all these radioactive waste before it comes safe. Right, like recently, Japan, they released a lot of all the nuclear waste into the river, right? Right, they did the calculation already. They say that after so many half-lives, right now throwing this shit into the river is not going to kill anybody. But obviously, because humans are very skeptical beings, right? Now everyone, all the sushi parlors, they're tanking because they say, "Hey, sushi from Japan or no? From Japan radioactive waste in the river later I become Teenage Mutant Ninja Turtle," so they stop eating that. That's why they tank the sushi parlors. But I see now they're picking up already the sushi parlors. Okay, everyone's like, oh, should be fine in one night. But if right, there was actually some form of radiation, it would take up to years for it to actually see whether it's safe or not. Anyways, no one cares right now. Eat first, die later. But anyways, back to this. It also enables doctors to use radioactive tracers. Radioactive tracers are literally pumped into your body to see where the clot is or maybe a cancer cell is. Okay, then they'll detect, they'll follow the tracer. And it's stuck here already. I know that there's some clog here. Clogging, I mean. Okay, but anyways, that's the application of half-life. Okay, everyone? Anyone's got any questions? Good. Attempt these 3 questions to understand a basic understanding of half-life. Sorry? Video? Oh. Not important. Do the question.
So,
Maybe starts off with 100%.
会50啊，
52哦，25啦。给我 timeline 啊，midday 是12点吗？
哦， yeah, 3 hours.
hours 有几多个 half life？ OK，这个是有点几多？一个 half life 9个小时。
1个小时。
哦。喂 everybody. So, I noticed most of you guys did question number 3 right? The question number 2 wrong. Why? If it says that a radioactive substance has a half-life of 30 minutes, right? It starts off with 100%, right? After one half-life, which is 30 minutes, it will become 50%. After another half-life, which is another 30 minutes, to become 25% left, right? Which is 1/4, right? I think everyone did this correct, lah. Right. The second one, it says that another substance has half-life of 3 hours, 100%. After 3 hours, 50%. Another 3 hours, which was the 6 hours, 25%. But they ask how much have decayed away. So actually, how much decayed away? 75%, right? Which is 3/4, right? I think almost everyone got it wrong for this one. Read. You have to read the question properly, by the way. This one actually, I purposely put this here because the exam sometimes does this. They'll ask how much have decayed away instead of how much is left. Pay attention to the question, guys. You will lose marks for this. And then this one here, it says that a researcher measures 200 counts per minute, and at midday means to say 200 counts per minute at 12 o'clock. Then at 3 o'clock, there was 25 counts only. So if you draw the arrow chart, it goes to 100, and then it goes to 50, and then it goes to 25, right? Your thought process should be something like this. Here to here was a total of 3 hours. In 3 hours, there was a total of 1, 2, 3 half-lives. And logically speaking, one half-life, yeah, must have been 1 hour, right? Which makes sense, because 12 o'clock, 1 o'clock, 2 o'clock, then 3 o'clock already. Okay? In your exam, if they don't ask about background radiation, half-life calculation is literally very straightforward. Most of you guys should be able to calculate and answer the question properly. But in reality, most of the time, they include something known as background radiation. Okay, which I purposely skipped here, guys. If you flip back to the first page here, there's something known as background radiation. Okay, so what is background radiation? Do you know that background radiation states that no matter where you go, where you are, there'll always be some form of radiation, even in this room itself. The standardized background radiation that you always see in your exam is somewhere around 30 counts per minute. Somewhere 30 to 50 counts per minute, depending on the question. It means to say human beings have already accustomed their body to this form of background radiation. It's not going to kill us. In fact, it doesn't affect us at all. Okay? It's not going to kill us at all. In the exam, if they ask about background radiation, they could ask 2 ways only in background radiation. Number 1, where does background radiation come from? Which, I say, the most common answer is cosmic rays. Cosmic radiation, literally from the space radiation inwards, contributes to the background radiation. Other common examples of sources of background radiation are like soil, which can be used to make rocks, which can be used to make building materials. They're actually all the same thing. But if you wrote either one of it, it's acceptable. Even the air is providing some form of background radiation. Okay, this one you must know. Always ask in your exam one. This is the first one that they ask in terms of background radiation. They'll ask you what is it, which you say they're always present, and randomized one, it actually fluctuates a little bit. So maybe at this point here it's 29, 30, 31, 28, 30, 32, then so it keeps fluctuating up and down, up and down, up and down. Okay? And it's always there. It's not going to kill you. Okay, and the other way they will ask is basically calculation in terms of background radiation, which I have this little slide here to show you. If you look at this question here, I'm gonna make this full screen. Oops. For now. Okay, everyone. If you look at this question here, right? Oh wait. Oh.
Count off.
Yeah. It's offline. Whatever. Hey, everyone, read this question here. Read this question for 2 minutes or 1 minute. I'll read faster, everyone. I'll explain how to do it. I don't know. It's not that complicated. There is testing. So when there is opportunity, at first, there's some problem with succeed. One hour. You finish reading? What, the final answer? No, it's not. Okay, everyone, listen up. So in this question here, right, there are a few useful information, right? First and foremost, it says that with no radioactive sample, the scientist records a background radiation of 40 counts per minute. So nothing was there, but there's radiation now, right? Let's show you the screen. Okay, with no radiation, nothing there, the detector, which is most likely the GMQ, detects a count rate of 40 counts per minute. Okay, that's the first thing. Then after it says that he brings a radioactive sample close to the detector, and right now the count rate increases to 200 counts per minute. Okay, after 24 hours, the count rate is 50 counts per minute. Oh, sorry, 24 days. The count rate is 50 counts per minute. They ask you to calculate the half-life for your radioactive sample. It's good to have a picture in your head, guys. The first thing you should know is that without anything on the table, this detector already counts 40 counts per minute already. So in order for this thing to count 200 counts per minute, how much should the radioactive sample be? 116. Right, because when this thing counts 200, this thing is actually only 160. So I want to say is that background radiation does not go through half-life decay. If you divide 2, that thing, right, the arrow diagram that I've been drawing so far, it only occurs in this part here. It doesn't occur here. No, it doesn't. Okay, so how will I be able to get 50 counts per minute? How can I, at what point of time can I get 50 counts per minute? If you were to draw the arrow diagram, right? This thing here, after one half-life, how much? 80. 80 plus 40, will it be 2, will it be 50? No. So after another half-life 40, right? Plus 40 will become? No. 20 plus 40 will become?
So that's 4 half-lives.
So how many half-life of this? If when it decay until 10, only I can see that it's going to be the 50 count, right? Because ultimately it's I wanted it to be 50 counts per minute, right? Right. So I know that at this point of time only I can read these 50 counts. So after I ask myself, hey, how many half-life for this? 1, 2, 3, 4 half-lives in the span of how many days? 24 days. So 24 days was 4 half-life, then obviously 1 half-life. It's 6 days. Alright, so my answer is your half-life is 6 days. That's your answer, Robinson. 那你一样哦，这个你怎么样 justify 除二哦？哇，这样子你会很 lucky 哦，刚刚好啊。But it doesn't justify the working. Okay, everyone. This is how they ask about background radiation in terms of calculation. But don't worry, later got a lot of exercises for you to do. Okay. Yeah, everything else. Now, these here are the applications of alpha, beta, and gamma particles. In terms of alpha particles, if they ever ask, you can say it is a smoke detector. It is used in between the smoke detectors. When the smoke pass by, right, the alpha particles cannot pass through already. So what's going to happen is the alarm is going to ring. So alpha particles can be used in smoke detectors. Beta particles is more commonly used in a lot of industries. For example, the thickness of the material and also the level of the liquid.
就是去你出有
因为它 extend 掉。Okay. In terms of beta particles, they're used to measure the thickness and also levels of liquid. You know, like for example, Milo powder. How every Milo powder can is the same level, right? It's because on top here there's a beta detector, right? The machine will keep pumping Milo downwards here, and the level is going to feel right. as it fills until that specific level, the beta particles will be blocked by the Milo powder, and then as soon as this detector cannot read the beta particles, right, it will send a signal to this machine to stop pumping in the powder already. And then it will just like level there. Like for example, this thickness here, it's the same application now. It's a bit hard to explain, but please read through it. Or if you want me, I can show you a video later on if you don't understand. But please read through this page, guys. If you talk about alpha particles and beta particles, usually is these two things on thickness of the material and water levels. And then if you talk about gamma, usually it's for radiotherapy. Okay, fight against cancer. Yeah, chemo. It's going to be gamma radiation. Okay. And finally, this last part here is literally common sense, but please read through it because this one also comes on your exam once in a while. They say only, actually is the concept is Inhua emits what's called electromagnetic wave, microwaves, right? Microwaves is part of the electromagnetic spectrum that is the same as gamma. So a lot of people bullshit and say that, oh, you put this phone next to you while you sleep, there's a lot of radiation that comes out and gets a chance. Not sure about that, didn't read any research on it. But I know for a fact that microwave radiation, while it can be harmful, it has to be a very, very, very high dose for it to be harmful. Right? So I call bullshit out. The charging phone one, didn't read much about it, but to my understanding, also bullshit out. But I didn't read much about it, so don't take my word for it. Okay, but to my understanding, it's bullshit.
Let's say for
the whole thing.
let's say into lessons.
Yeah, 2 lessons. Okay, please make sure you read through everything though. Like these 2 pages. It's not that hard to understand, but it's good to read through so that you have that information in your head, guys. But it's very easy, it's very makes sense. Especially this one. Yeah, of course, everything else. Until you see 6.1. Next week onwards, I think we'll be doing some revision up until the radiation chapter. And then like probably we'll do revision. Most likely, guys, the last 2 weeks of December, there's no class. Very, very likely the last 2 weeks. Yeah, which is the last 2 weeks. Right.
That's a people thing.
Charity night, what? Doing what? Raise funds up. Oh, 几个号 ？Y 位可以进去啊？ 算了啊。But no, this last 2 weeks no class already. 14. Oh, yeah.
今年是我第1年是类型，上了为什么是在完人节？Welcome to the jungle.
你先记这个好
For sure. Tailors. Some say the haters gonna hate. Yeah, okay. Guys, everything else here is from 我想最后2个礼拜没有上课 of December. This last 2 weeks, no class. December 15 onwards, no class. So 你就可以 enjoy 了。只是要上工 哎，看你的样子我就知道了，你就上到3行你就被 enjoy 了。放紧，继续，放到明年了，and then 放假到明年，哇，enjoy life 啊，enjoy life，baby。